Hi, my name is Piotr, and I will tell you why people should be more interested in laser optics by explaining computer-generated holograms. Just a quick overview, I will say what is a hologram, how it is created, a basic one, your TV and its relation to a hologram. I will say a few words about the beam modes and GS algorithm. I will show you really nice results, and I will also tell why else people should be more interested in laser optics. Well, let's start with question, what is a hologram? So hologram is a 3D capture, 3D appearance capture of an image that contains all the important information, which is wavelength, amplitude, and phase. Remember these three because I will be using them often. If you compare a normal picture, like a 2D picture, it contains only amplitude and wavelength. So if you take it in your hand and you just like rotate it, there is not much you can see. If you take a hologram, you can actually look at the picture or the object at different angles. So how it is created? Well, you have a usually monochromatic light source, which is maybe a laser, and the laser beam is then split into half by half mirror or a beam splitter. One of the laser beams will be used as a reference light, and the other one goes to object. When it interacts with the object, it records all its features, such as depth or size. And if you then cross the two lasers together, you can extract the information and actually create the hologram, usually on a photographic plate. One may ask, why bother? Well, my personal favorite one was proposed by one of my friends, and it is to create a hologram of your mom's car so she doesn't know you took it. But just to explain, there are different types of holograms. Not all of them needs to be 3D. So for example, when we go to the computer-generated holograms, they won't appear 3D. And in everyday's life, we have a lot of holograms around. Do you have, or does anyone have, oh, I can bet everyone has a credit card or debit card, right? Have you ever seen this thingy here? This one? That's not a really nice sticker. That's a hologram, a high security hologram that contains all the information about your car provider and your account. Okay, let's go back to the PC, was it, yeah? Right. Now we go to the computer-generated holograms. To create a computer-generated holograms, we'll need a few tools. One of them is TV. I said in my abstract that I will tell you how to use your TV to generate, to force the laser beam into a shape, and you can't. Sorry. Well, you might, but creating a laser beam of this size wouldn't be very cheap or like effective, unless you wanted to shoot down some satellites or something. But what you can do, you can use the technology that is used in the TV. Does anyone knows what the LCD stands for? Anyone? Liquid crystal display. Exactly. So we'll use the liquid crystal device that is called spatial light modulator. Well, what is a liquid crystal? Just quickly, it's something between the conventional fluids and solid. 1991 Nobel Prize for discovering it. So. How it works, you have crystals in your TV that are basically randomly distributed in nematic phase. If you apply electric field, they start to align, forming a picture. Probably you have even noticed it when you like watching a movie and the screen is going from bright to very dark. Have you seen like changing pixel or something? Now you know how it works. Okay, we'll need another tool, which is our laser. What is a beam mode? So beam mode is basically just an intensity profile that can be seen in a cross-sectional laser. So if you like just stare straight into it, you could see different patterns, and they have different properties. A few of them. So the first row is the theoretical one. So it's like a Hermite-Gaussian, Laguerre-Gaussian, and Bessel. And the bottom row, as you can see, it's our experimental results. We're kind of there, but probably we could use some more time to work on this one. And like I said, they have different properties, but the most interesting one is the basal beam, which can regenerate itself. There is only one tiny problem with it. If we want to use it in real life, it requires an infinite amount of energy. But we can make quite reasonable approximations to it. Right. So we have our TV, we have our beam, and the problem with creating computer-generated holograms is that you are not allowed to change the amplitude or the wavelength. The only thing you can play with is the phase, and that's where the Gerchberg-Saxton algorithm comes. Without going into detail how it works, I will just tell you what it does. What it does, it produces this, which is called a phase mask, and a phase mask allows you to manipulate the phase of a laser, so you can actually change the shape of it. So you input image, phase mask. It looks kind of like snowy TV screen, like in old TVs. If maybe some of you remember, I'm so old. Right. So we have our 3 tools, and now we need, of course, some laboratory setup. So our laser, which goes through some lenses, filters. You remember TV? It's just here. It's like a tiny bit there. Our Gerchberg-Saxton algorithm that displays phase mask is just displayed here. That's where it affects the laser. And then we have our hologram. Ready for results? Okay. Oh no! How does it work? So you click it. Okay. Looks like it doesn't work, but it is dancing cat. It is that I have a phone with me, so I can show you on a break. Actually, it dances and it's really nice. But so it's a fun result, and our project was really fun, one of the best ones probably that year. But this bit here has really serious consequences, because using this technology, you create optical tweezers. And optical tweezers are very widely used these days, and believe me, these dots that you can see here, they are single atoms that are held in position or rotated. So basically, using optical tweezers, you can manipulate the single atoms. And this has a lot of uses. Just to name a few of them: genetics, immunology, chemistry. You can use any biology students here? No? Oh, there's one. You can use optical tweezers to probe the red blood cells aggregating force. I don't know what does it mean, but but you can do it. Right. So optical tweezers, very useful. What else is there? How else we could use optical laser optics? What else we could do? So we could, for example, build a really big laboratory, and, for example, observe the gravitational waves. How? Well, does it look familiar? Laser, beam splitter, it goes one way, another one, and instead of photographic plate here, you have a detector. So very similar principle to the one how the basic hologram is created. Okay, so just a few words about this one. Nobel Prize 2017 for observing gravitational waves. The signal that was observed was this. Does anyone want to count the zeros? No, okay. Just 10 to minus 21 meters. So it's very, very, very sensitive. And that's why we could observe it. What I'm doing this year, and actually Glasgow University as well, and Stanford University in USA. So this field is really hot now because of the discovery. I'm working on this bit here, mirrors. So we are measuring the laser absorption in end mirrors in order to develop more sensitive ones, better ones for future gravitational waves. And the dancing cat was a team effort. So I would like to thank you all the guys on the picture. Some of them are sitting in here, so you can ask them about the cat as well. And basically, do you have any questions?